In this next part of section 4, we're going to verify that two functions are inverses. So given two functions, can we say yes or no, these two functions are inverses of one another? So let's use the same two functions that we had above. So the first example we'll look at is with the function y equals 4x plus 2. And we already found the inverse. So we know that y equals x minus 2 over 4 is the inverse of this function. But how can we verify that? Well, let's think about this for just a second. If we plug in a 1, right? If we plug in a 1 into the first function, 4 times 1 is 4, plus 2, it spits out a 6. And if we plug that 6 back into the inverse function, 6 minus 2 is 4, divided by 4, spits out a 1. All right, so if we plug in some value into the first function, it gives us an output, and if we put that into the inverse, it should give us what we started with. But checking just one point isn't enough. We need to know that this works for all pairs of inputs and outputs. So if we choose any x, and we plug it into that first one, it spits out some y. And if we take that y and plug it back in, we should end up back with that x. Okay, so if we do both functions, plugging in any x should just give us x. So what we do is we're going to compose the two functions, and we talked about composition in section 3. That's when we take an entire part of one of the functions and plug it in to the other. So we're going to compose the two functions. So we would have y equals 4 times x minus 2 over 4 plus 2. And so there essentially we're doing the second function and the first function all together. And when we do both of them for any x, we should just end up with x. So we simplify this. And here we have times 4 divided by 4, so those cancel. So then we have the x minus 2 plus 2. So minus 2 plus 2, those cancel, and we end up with just y equals x. And if that's the case, then these two functions are inverses. If we compose two functions and we get y equals x, then they are inverse functions. So our second example here, using f of x equals 2x cubed plus 1, we found that its inverse was cube root of x minus 1 over 2. So let's go ahead and compose those. So we're going to take this whole piece and plug it in for x in the first equation. So we have f of x equals 2 times a cube root of x minus 1 over 2. And that whole thing is cubed plus 1. So start simplifying things. A cube root cubed, those are two opposite things, right? If we square a square root, those undo each other. So cubing a cube root undo each other. So now we're just going to be left with 2 times x minus 1 over 2, because the cube root of x minus 1 over 2 cubed is just going to be x minus 1 over 2. And that's not cubed anymore. So that should just be 2 times x minus 1 over 2. And same as last time, we have times 2 divided by 2, so those cancel. So x minus 1 plus 1, minus 1 plus 1 is 0. So f of x equals x, right? If we plug in some x and we compose and we do both functions, we end up again with x, right? If we follow directions from point A to point B and then follow the directions back from point B to point A, we should end up at point A. We should end up with what we started with. So that would verify then that those two functions are inverses. The last thing we're going to look at in section 4 is the horizontal line test. So you might remember, I think chapter 1 or chapter 2, we talked about something called the vertical line test. The vertical line test is used to test whether the graph is a function. Because remember, a function, for each input, you can only have one output. So the vertical line test, let's look at A right here. The vertical line test, you take a vertical line and pass it all across your graph, and it should only hit one place of your function at a time, right? Because if we are only hitting it at one spot at a time, then whatever that input is only has one output. So all of these pass the vertical line test. So these are all functions. The horizontal line test is going to determine whether the inverse would be a function. So if the inverse also has one output for every input. So one interesting thing about inverse functions is their reflections over the line y equals x. And that's hard to see with A, so let's look at B. The line y equals x is just that diagonal line. The inverse of that reflected would look like this then. Okay, it would flip over that. All the x's get switched with all the y's. Okay, so that's what the inverse function there would look like. So the horizontal line test, we take and pass a horizontal line across the entire function, and if it hits only one point at a time, that tells us that the inverse would be a function. So this one passes the vertical line or the horizontal line test, and its inverse is a function. Now let's look at B. If we pass horizontal lines across there, there's lots of places where it's hitting more than 1 point at a time. So this one fails the horizontal line test, and its inverse is not a function. And again, let's look at what the inverse would look like on this. The inverse would be a sideways parabola, which would not pass the vertical line test, so it's not a function. So basically, you're just doing the vertical line test, but sideways, right? So lastly, on C, pass horizontal lines across here. At any given point, we're only hitting one spot at a time, so this one passes, and the inverse is a function.